Okay. So let's just quickly talk about probability. So what it is and what we kind of know what it's about is the chance of something happening. Do you agree with me? Like if we flip a coin, what's the chance of the coin falling on heads or tails? Okay, now to determine that probability, we always say that it's going to be the positive outcomes divided by the total number of outcomes. That's the main equation that we use. So let's just quickly write it down. Is it possible twice or once? Possible. One is two like that. Okay. Okay, now this is not at all what we are going to work with in grade 11, but I just need to give you some background so that you understand what how probability works. Okay, so if we have a dice that we're going to roll, and I ask you what's the probability of getting a number 2, how many number 2s are there on the dice? 1. How many possible numbers are on the dice? 6. So the probability will be 1 out of 6. If I ask you what's the probability of getting an even number, how many even numbers are on the dice? 6. No. 2, 4, and 6. It's 3 numbers. How many possible outcomes are there? 6. So it's 3 out of 6, which can be simplified to 1 over 2, and it can be written as a decimal, 0.5, and it can be written as a percentage, which will be 50%. Now, I'm not going to get into it with you about how to convert a fraction to a decimal to a percentage. I'm sure all of you know that, and you should know that by now. Okay, but the bigger picture about probability comes in when where we use it in the real world. Like for example, if you want to calculate the number of possible outcomes, example, we're going to flip a coin and we're going to roll a dice. We want to see how many different outcomes we can get. Now, how many different outcomes can I have when I flip a coin? 2. How many different outcomes can I get when I roll a dice? 6. Now the number of possible outcomes, let's just quickly draw a tree diagram. Do you know what a tree diagram looks like? Let's just write tree diagram so that when you study you know this is a tree diagram. So we're going to take the coin first. We've got 2 outcomes, right? What can the 2 outcomes be when I flip a coin? Heads or tails? Now after I flip the coin, if I now roll the dice, how many options can I have when I roll the dice? 6. Does it matter whether I got heads or tails? Does it influence the outcomes of the dice? No. So I've got 1, 2, 3, 4, 5, 6. It can be 1, 2, 3, 4, 5, 6. And if I got tails the first time, I still have 6 outcomes with the dice. It's 1, 2, 3, 4, 5, 6. And just so you know, the singular form for a dice is actually a die. D-I-E, like die. So just take note of that. Whenever they give you a question in a question paper that's about a die, they will refer to it correctly as a die. Okay, dice is 2. Okay, so this is a coin and this is a die. So the outcomes I can have here is heads 1, heads 2, heads 3, heads 4, heads 5, heads 6, tail 1, tail 2, tail 3, tail 4, tail 5, tail 6. Okay, so what's the total number of outcomes that I have there? 12 outcomes. Now, if we wanted to calculate that without having to draw the tree diagram, we take the number of outcomes we get from the coin, we take the number of outcomes we get from the die, and we multiply with them with each other, and then I get the total number of outcomes. 2 times 6 gives me the total outcome of 12. Now, when we look at probability in real life, let's take a look at number plates. Have you noticed that the Gauteng province's number plates are different from the Free State? Not just the numbers, but the format. Have you noticed that? Now, in previous years, Gauteng was the same as us. It was letter, 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 number, 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 and then GP. Now they are letter, letter, number, number, letter, letter, GP. Whereas Free State, we are still 3 letters, 3 numbers, FS. Okay. Have you all noticed that? Have you given it a thought? Why they have changed it? Now let me quickly show you. You agree with me that the Gauteng province has got way more people, way more cars, everything more than in the Free State. Or in other provinces for that matter. Now, the possible combinations that we can get from the Free State number plates. Okay, obviously there are some more technical points, but I'm just not going to use all of them now. When we take our first letter, it's letter, letter, letter. The first letter can be any letter except for a, a consonant and a vowel. Is it a vowel? No. Okay. So A, E, I, O, U. Otherwise, it will spell maybe a swear word accidentally. That will be your number plate. So the vowels are left out. Okay. So how many numbers are there from A to Z? 26. Leaving out 5 numbers will be 21. How many letters can I use in the second row? Once again, 21. Last one, 21. In actual fact, with these ones, the first letter, we also are not allowed to have G in it, because G stands for the government cars. So that would actually be 20, but that's what I mean. I'm not going to get into that totally now. It won't have such a big influence. Okay. Then we have a number, and a number. How many different numbers can you have for the first number? Can 0 not be an option? It's 10. And the second number 10 and the last number 10. So if I wanted to calculate how many different number plates we can make in the Free State, because remember we can't replicate it, no? I'm going to have to say 21 times 21 times 21 times 10 times 10 times 10. Now I will take the calculator and work it out for you. 21 times 21 times 21 times 10 times 10 times 10. That gives me an answer of 9,261,000. Okay, those were the number of number plates available in Gauteng as well. And then they ran out of number plate combinations. That's why they had to change the format. Okay. Now, you must go and take a look, when you're driving around, or when you're walking around, whatever. Go and see if you see a brand new car. Go and look at what the number plate starts with. The first number or the first letter it starts with. I think it's H roundabout there. It might already be J. That's only where Free State is now. So they've still got a long way to go. They're about halfway through the alphabet with number plates. So there are still a lot of options there. But now, this was Free State. Ne? Let's look at Gauteng. Now after they ran out, they now have letter, letter, number, number, letter, letter. It's 21, 21. And now, do you agree with me? Because it's only 2 letters, né? We can easily have a vowel in there as well. But we just leave it as it is here, and then 10, and then 10, and then 21, and then 21. We'll keep the playing fields level. So I'm going to calculate it for you. 21 times 21 times 10 times 10 times 21 times 21. 19,448,100 options of number plates. So that's like more than 10 million number plates more than we have available in the Free State. And that's where probability comes in real life. Okay. So it's not about what the odds are of you winning the lotto. Okay. Now, we need to look at different concepts, different ways of calculating the probability. So, for instance, when I say you brought a kosblik to school, né? And you packed a banana and a strawberry and a broodjie and a packet of chips. There are those 4. Okay. If we say that you close your eyes and you fairly choose one without feeling them out, you just choose one. What's the probability of choosing a banana? We had 4 options. How many of them are bananas? 1. So it's 1 out of 4. But now you take out the banana and you eat it. Do you see that that now influences your probability for the next choice? Okay. So these options influence each other. Whereas with the previous one, with the coin and with the die, they don't influence each other. Whether you got head or tails, it doesn't influence getting the next outcome. But whether you chose a banana or not influences the next choice that you're going to make. Because now for the next choice, you only have 3 options. What is the probability of taking out a banana? Again, how many bananas are in there? 0. So what's the probability? 0 out of 3, which is 0. What's the probability of taking out the broodjie? 1 out of 3. Okay. Now you've eaten the banana, you've eaten the broodjie. What's left is a packet of chips and the strawberry. So what's the probability of taking a banana? 0. What's the probability of taking a strawberry? 1 out of 2. So you see the chances are getting bigger and bigger and bigger and bigger and bigger. Okay? So you took the strawberry. Now what's left is a broodjie. What's the probability of taking a banana? What's the probability of taking a broodjie? 100%. 1 over 1. Okay? And do you see that when we started, the probability of taking a broodjie was also 1 out of 4. But in the end, we took it last. Okay? So that's what I need you to understand. It's not about what you eventually get. It's about the different options. How many different outcomes do we get? Okay. Now, because you missed grade 10 probability, we've got some catch-up work to do. And I want us just to write down this work, and then we will talk about it and explain it to you. Okay. So let's just make a summary. Do you know what a Venn diagram is? Not. Okay. I just want to know. Okay, I just want you to draw the Venn diagram. I'm going to explain it to you. That must be a P, sorry. I'm just going to draw a line first. You all done? Not yet? Done? Okay. Alright, now I'm going to show you a PowerPoint just to explain this to you, what we've written down. Okay, probability. Solving probability problems by we can use a Venn diagram. So that was the circle one that you just saw. Now we're going to explain it to you. Okay. The two-way contingency table. Have you heard about that? Okay, I'm just quickly going to go back to writing here. I just want to give you an idea. You don't have to copy it. So when you draw a contingency table, we will, for example, say you have got you've got 3 shirts and you've got 5 pairs of pants. Okay, so you've got pants 1, pants 2, pants 3, pants 4, pants 5, and you've got shirt 1, shirt 2, shirt 3. How many different combinations of clothing can you get? So you can wear shirt 1 with pants 1, shirt 1 with pants 2, shirt 1 with pants 3, shirt 1 with pants 4, shirt 1 with pants 5, and so on. You will complete the whole table. So here you will have shirt 3, pants 4. You get the idea. Okay, that's a contingency table. We have a tree diagram. That's the one that we just drew. And then the counting principle is only for grade 12, so we're not going to look at that now. The baseline knowledge, the probability of an event, the number of outcomes in A over all possible outcomes. So that's what we wrote down. The positive outcomes for whatever they are asking. over the total number of outcomes that we have. Okay. In this case, I want you to take note of the way we write it. We wrote down P bracket A and P bracket B now. That means the probability of getting that specific option. Okay. The probability of getting heads, it will be P bracket H. The probability of getting tails, P bracket T. You understand? Okay. Now, this one shows a Venn diagram. This represents the space for event A. This represents the space for event B. Now, I want to explain this to you by your subject choices. Okay. For example, if you have to choose, if we have to take the learners who chose maths or math lit, that would be mutually exclusive. That means you can only have maths or you can have math lit. Those two circles can't cross each other. There can't be some kids who have math and math lit and some kids that have math lit and math. They are exclusive from each other. Do you understand that? Okay. If we look at learners who have accounting and mathematics, or let's say accounting and math lit, that will be easier. We can have learners who only have accounting and not have math lit. Remember, we're not talking about maths now. So they have accounting and some that only has math lit. But there are some learners that have math literacy and accounting. And that's where the cross happens, where the two circles cut each other. So let's say this is math lit, this is accounting. These will be the number of learners that have math lit and accounting. Okay. This brings us to a funny way of talking. Because let's say there it said 30, there it said 10, and inside of that one it says 5. Okay. 30, 10, 5. If I ask you how many learners has math literacy, you cannot just say 30. You have to say 30 plus 5. It's 35. If I ask you how many learners has got accounting, you would say 10 plus 5, that would be 15. But if I ask you how many learners does not have accounting, how many learners does not have accounting? Everything in this circle is accounting. So the learners that do not have accounting would just be this space on this side, which would be 30. Do you agree with me? It can also happen, there are some learners who have who don't have math lit and they don't have accounting. Are there some of you in this class that don't have accounting, or do you all have accounting? Who doesn't have accounting? Okay. Those of you whose hands are up now, you wouldn't fit into either circle, right? You wouldn't go with math lit, you wouldn't go with accounting, you wouldn't go with math lit and accounting. So your number would be on the outside. Let's say there's a 20 on the outside, and I repeat the question. How many learners do not have accounting? We would say the 30 here and the 20 on the outside. So only the ones included in accounting circle would be accounting. Do you agree, if we know that the total number of learners is, for example, 65, we can just take the circle, this value, and subtract it from the total. That would give you the answer as well. Okay, that brings us to an equation where they say the probability of A, of whatever I'm asking, is equal to the total number minus the probability of not A. Does that make sense? The probability of the learners who has accounting is the total number of learners minus the learners who don't have accounting. It makes sense, but the way it's written is confusing, and that's what makes it a bit difficult. Okay, so here's a Venn diagram with three things. So we can make a Venn diagram with math lit, and accounting. Okay? There will be learners who has math literacy only. There will be learners that have math literacy and accounting. There will be learners that have accounting and maths. There will be learners that has math only, and let's just pretend there will be learners that have math and math literacy, if we had chosen another subject now. And that one right in the middle will be learners who have all three subjects. And do you understand that's true? If I had taken maths, accounting and life sciences, we would be able to draw a Venn diagram like this. Do you agree? Where some have only one of the subjects, some have two of the subjects, and some have all three of the subjects. Okay. The shaded area presents A and B. Okay. So you must have maths and accounting. Both of them. Then you're that one in the middle. Now just take note of the way we can write it. It's A and N. Ne? N. For and. That's how you remember it. Okay. The reason I'm going on about it is you're going to get confused about and or. And, it has the N in for and. Okay. Or is when it's upside down. So here we say the shaded parts represent A or B. Okay, so that's everything. Who has maths or accounting? Then it will be everyone in that circles. Who has maths and accounting? Only the ones in between. So it's a play of words. You have to concentrate. Okay. There, the upside down one that looks like a bucky goes with or. Okay. The N goes with and. And they also show you there that it's plus and times. Okay. Next one. The addition rule. A and B are mutually exclusive. Mutually exclusive. So that means you can only have maths or you can have math literacy. Okay. Mutually exclusive. This one, A and B are not mutually exclusive. We call it inclusive events. So what the sum is here, if I want to know how many learners has got maths or accounting, you can just take the number at maths plus the number at accounting. It will give you the total number of maths and maths or accounting. If we have an inclusive Venn diagram, and I ask you how many learners have got maths or accounting, you can take the number of maths learners plus the number of accounting learners, but you're going to have to subtract the ones that are in between. Otherwise, you're going to add those numbers twice. Do you agree with me? Okay. That's where that equation comes from. Probability of A plus the probability of B minus the probability of A and B, the one where they are in between. Okay. Are you happy with that? You understand that? Yes. Okay. Consider the probability rule. Probability of A or B equal to the probability of A plus the probability of B minus probability of A and B. Is this, can you see, do you recognize this equation? This is the equation for inclusive, for the one where the two circles intersect each other. A and B are inclusive if the probability of A and B are not equal to 0. So that means if it exists, if there's a number in between that they share, there is an intersection. So you know that by now. Mutually exclusive, that's when they don't intersect. That's when A and B, the cut, is equal to 0. It doesn't exist. You can only have maths or mathlet. Complementary events. Complementary events are mutually exclusive and exhaustive. Now we haven't spoken about exhaustive. If we consider the Venn diagram that I started with, the math and the mathlet, that would be a Venn diagram that's exhaustive because you must have either maths or mathlet. There's no one that can be outside of those circles. You must be the one or the other. But if we take maths and accounting, there will be learners outside. There will be learners who don't have mathematics and they don't have accounting. When it's math and math lit, that's when we say it's exclusive. But when there's someone on the outside, then it's not exclusive. That means all of the people hasn't been used in that two circles. Does that make sense? Okay. And a complementary event is when everyone is in the two circles and they don't cut each other. So it's math and math lit. That's a complementary event. They don't cross and there's no one left out. That is where we use that probability. The probability of not A, of not accounting, will be all of the learners, of not math, will be all of the learners minus the math lit learners. So if If Mr. Van Zyl wants to know how many kids do I have in the math class, but he can't find me. He can't get hold of me. He knows there are 100 grade 11s. Then he can go to Mr. Van Zyl and ask him, how many learners do you have in math lit? And if he says he's got 50, then Mr. Van Zyl can do the sum and say 100 minus 50 is 50, therefore there will be 50 learners in maths. It makes sense, but it's difficult because it's written like that. And we don't know what it means. Okay. So not A is written A with a little thingy there at the top. Okay. The complementary rule, there it is. 1 minus the probability of A gives me the probability of not A. Words. Exactly 1 means only 1 in any order. Exactly 2 means only 2 in any order. At least 1 means 1 or more in any order. At least 2 means 2 or more in any order. Simultaneous means dependent events. Same as without replacing. Okay, so that would mean if you remember the Kospluk situation, né? If I say you take 2 items, and your one item was a banana, then that does influence the other one. They depend. It depends on what you take with your one hand, what you would take with the other hand. Although it happens at the same time, they depend on each other. Does that make sense to you? Okay. Independent events. One event has no effect on the probability of another event. Okay, so the probability of A and B, probability A times probability B. That's what we had with the coin and with the dice. Okay. You can use the product rule there. That's the one that we started with. Dependent events. One event has an effect on the probability of another event. The product rule for dependent events. If A and B are dependent events, then you would say the probability of A times the probability of B over A. We're going to look into that after a while. But remember, when they are not dependent, it's just probability of one times the probability of the second one. That was what we did with the coin and the dice. When they are dependent, it's the probability of the one times with the probability of B over A. Okay. Probability of event B after event A has occurred. Right, the summary for the Venn diagram. That one in the middle is A and B and C. When none of them is colored in, it's none. When all of them is colored in, that's A or B or C. So you understand the difference between or and. That's just the same. Okay. Let's do this example. Can you see those numbers there? Should I try to make it a bit bigger? Don't know how to get rid of this. Okay. What is the probability of getting A and B and C? Probability of A and B and C. So you have maths, you have accounting, and you have life sciences. 5. Okay. 5 out of the total number of people. Okay, so always remember that a probability must be a fraction. So we don't have the total here, but I will tell you it's 350. So it's going to be 5 over 350. What's the probability of getting A and B, but not C? A, B, not C. 10. Do you all understand why it's just 10? That's the only one that is A and B. This 5 includes C. This 10 includes C. This 15 includes C. That 110 does not include B. And this 85 does not include B. Okay, so we want A and B, but not C. Then it's 10. What's the probability of getting A or B? Okay, A or B. Okay, let me ask you. This 85, is A in there? Yes. Okay, so we'll use a calculator. We've got 85. The next one, that 10, is A or B in that 10? That 110 is A or B in that 110? This 15, is there A or B in that 15? Yes, remember that combination means you've got B and C. Do you understand? Okay, so we have to add that 50. They are not saying A and B, they are saying A or B. That 5, does all of those 5 learners have math and accounting? Never mind what else they have. Do they have math and accounting or accounting? Yes, because it's part of A, it's part of B. So it's plus another 5. And then this 10 here, it's between A and C. Yes, because those learners have math. It just doesn't have this one. Okay? So that gives me 235. Okay. What I could have done as well to get to the right answer is to say 350 minus 90 minus 25. Do you agree with that? Everyone? Okay. What's the probability of getting B or C and not A? So I'm going to go through it quickly with you. This one is B or C. This one is B or C. This one is B or C. The 25 is B or C. No, we don't want the 25. Sorry. It's not B or C. So it's this one 90, 15, 110. But everything that's part of A cannot be part of our answer. Because they want B or C, but not A. Okay. Okay. Now it's going to get hard where we have to make our own Venn diagram. So I want you to open your book. I want you to draw a Venn diagram like that. With 3 circles. Use a pencil. Make it big enough for you to see. I'm also going to draw one here and then we will try to fill it. Okay. Now when we want to make our own Venn diagram, we have to be careful. If we look at the first part of information, it says 28 like vanilla. Can I go and put a 28 there? Yes or no? Why not? You are right, you cannot put a 28 there, but why not? Thank you. It's possible to like vanilla and lime. Or like vanilla and, what's the other one? Raspberry. Or like vanilla, lime and raspberry. So you can never start on the outside. We start on the inside. Now let's look at what we have. We have 28 for vanilla, 25 for lime, 29 for raspberry. Neither of those three can I use. Ne? Can't start with them. 5 like all 3 flavors. Can I start with that one? Where does it go? Right in the middle. Okay, so put it right in the middle where they cross. It's going to be there. Next line. 7 do not like any of these. Where does that go? On the outside, anywhere on the outside. 11 like vanilla and lime. Vanilla and lime. 8 like lime and raspberry. 8 like vanilla and raspberry, but not lime. Okay, now let's think about this. How would you use the 11 like vanilla and lime? Vanilla and lime. If you look at the stars here, do you see they put a single star here by 8 like vanilla and raspberry but not lime? Do you think it's safe to start there? I think so, because they say 8 like vanilla and raspberry but not lime. So I know exactly where that one has to go. Can you tell me where that one has to go? They like vanilla and raspberry but not lime. There. Okay, so I can put in an 8 there. 8 like lime and raspberry. So lime and raspberry would be somewhere here. Can I put 8 there? Are you sure? What about the 5 that also like lime and raspberry, but they like vanilla as well? Huh? Don't they like lime and raspberry as well? That 5 that you started with, do they like lime and raspberry? Yes. They also like vanilla, but they like lime and raspberry. Now they're telling you 8 like lime and raspberry. Must I put in the 8? Or what must I put in there? 5 of the 8 that like lime and raspberry is already in that section. Do you see that? That is the whole section for lime and raspberry. Not just that part. This part, look at where that arrow is now. That is for liking lime and raspberry but not liking vanilla. The space for liking lime and raspberry is this space. So therefore, if they tell me that 8 people like lime and raspberry and 5 of them are already in there, I can only put a 3 in there. Now you know the catch for 11 like vanilla and lime. 11 like vanilla and lime. What must I put in there? 6. Now I can go to the big values. 28 like vanilla. You said I can't put a 28 there. What must I put in there? What do you say? 28 like vanilla. 9. How do you get to 9, princess? You subtracted these that you already have in there. Because just because you like vanilla doesn't mean you don't like the others. So I said Princess said 28 minus the 8 for liking vanilla and raspberry, minus the 5 for liking vanilla, lime and raspberry, minus the 6 for liking vanilla and lime. Let's just finish it. So that gives me an answer of 9. 25 like lime. So I can say 25 minus 5 is 20, minus 6 minus 3, that gives me 11. Are you happy? You understand? 29 like raspberry. So I'm going to say 29 minus 8 minus 5 minus 3, that gives me 13. And there you've drawn your first Venn diagram. That's what it's supposed to look like. Do you understand? Okay. When you come back tomorrow, we are going to start to practice it, okay? Guys, go and learn that words. It's very important. Go and learn the equations. And the way that we write it, please.